the previous video, we discovered that the modules of Hapta 67 are securely bound internally through the post-tensioning method, and we explored how the connections and bonding between modules were established. Additionally, we confirmed the use of high-strength grout and sealant in the finishing work, along with asphalt coating around the junction areas. In this video, we will explore waterproofing and windproofing for exterior walls, finishes for interfaces between modules, and finishes for the upper surface of the lower module, which serves as the terrace for the upper module. We will also look into methods and devices used to align modules horizontally and vertically during stacking, as well as devices used to verify alignment. Additionally, we will describe the MEP system within each individual module and its integration with the overall MEP system of Hapta 67. In the previous video, we briefly explored the methods used in Hapta 67 to overcome water leakage, including the application of such as asphalt coating and sealant. Today, we will use modeling to divide the areas and examine how the final finishes and joints were achieved in each section. We will look into Section A, where each module contacts the exterior, Section B, where modules connect with each other, and Section C, which concerns the terrace area. First, let's take a look at Section A. Section A is where the modules are directly exposed to the external environment. In the original Hapta 67, the walls had minimal insulation, leading to durability issues and leaks over the years. Additionally, the ability to block external air was inadequate, making it vulnerable to the harsh Canadian winters. These weaknesses were addressed in a major renovation in 2017. The existing concrete walls were stripped back and cleaned, removing some damaged wood and the old polystyrene insulation. 31mm liquid air and water barrier was applied. The barrier stops water and air penetration, but does not impair the movement of vapor. A Z-guard system was installed against the wall and insulation was added. Smart vapor retarder to allow the wall to dry either toward the inside or the outside, depending on the direction of the water vapor flow, which is directed by temperature and or water vapor pressures. The Z-guard system is a specialized exterior cladding system applied to the outer walls of buildings. It typically involves covering the exterior walls with a mixture of cement and gravel, known as gart, enhancing the building's protection from external elements and increasing its durability. The Z-guard system helps improve the robustness and longevity of the building envelope, safeguarding it against wear and tear over time, and providing protection from weathering and climatic changes. Ultimately, to control airflow and vapor drive, increase drying potential, and prevent moisture-related issues while better preserving the building envelope. The renovation approach described above was applied to Hapta 67. Next, let's examine Section B. Section B represents the area where modules meet each other, and most crucial finishing detail in this area is the perimeter. In this perimeter area, besides the sealant and asphalt coating mentioned in the previous video, protective mortar was applied to maintain integrity. Lastly, let's examine Section C, the terrace area. Each unit in Hapta 67 has at least one terrace, which is an important space. The primary concern here is how to properly drain water from the terrace. Without an adequate drainage system or proper finishing, maintaining the terrace would be difficult, especially during rain or when watering plants. First, let's look at the drainage system. The terrace is slightly sloped to direct water to a drain located at the corner of the terrace. This water flows into the MEP system pipes within the module, which will be explained at the end of today's video, and ultimately into the overall MEP system of Hapta 67. Next is the terrace finishing. The terrace's finishing begins with the installation of the roof, which forms the terrace itself on top of the module. The module that serves as the terrace's railing is then installed. Sealant is applied at the junction between the railing and the terrace to ensure a proper finish. Finally, the terrace floor is covered with treated wood for easier maintenance. Treated wood is advantageous because it is easy to replace if damaged and has a relatively short installation period. So far, we have examined sections A through C to see how the final finishing was done. However, even if the finishing is done well, if the modules are not aligned vertically and horizontally during the stacking process, resulting in gaps between the modules, it would be meaningless. Ensuring vertical and horizontal alignment is crucial not only for finishing but also for the overall structural stability. Now, let's explore how vertical and horizontal alignment was achieved during the module stacking process and how this alignment was verified. First, to align the modules horizontally and vertically during the initial lifting process by the crane, adjustable cylinders and adjustable trolleys sized to fit the modules were installed. Although all modules were of the same size, the walls of each module had different openings depending on their designated location. Therefore, the adjustable cylinders were adjusted to distribute the weight of the module accordingly. Secondly, the modules lifted by the crane were positioned using pre-calculated points grooves to maintain their alignment. These grooves served as the connection joints between the modules, ensuring vertical and horizontal stacking. Finally, once the modules were fitted into the grooves, the modules were secured by connecting the post-tension cables while maintaining their vertical and horizontal alignment. Just as the modules wouldn't fit properly into the grooves if they weren't aligned correctly, the post-tension cable connections wouldn't align if the vertical and horizontal alignment was off. Therefore, the vertical and horizontal alignment was verified both by fitting the modules into the grooves and by connecting the post-tension cables. Even after going through various verification procedures to ensure that the modules were perfectly vertical and horizontal, the stacked modules were finally checked using a level, as you can see in the photo. Finally, let's take a look at the MEP systems of Habitat 67. During the construction process of Habitat 67's modules, the bottom part of each module features a structural framework upon which the actual flooring, stepped on by residents, is installed. Beneath this framework, various cables, pipes, and ventilation shafts are installed. These components, including electrical outlets and ventilation controls, are positioned close to the floor, as seen in the photos, due to the presence of various MEP elements installed at the bottom of the modules. This subfloor is one of the Habitat's great technical inventions, a 300 mm deep space under the floor that provided for air conditioning equipment and ducts, plumbing, and electrical routing. It was conceived almost in innocence, a method by which we could insulate the cantilevering floors, distribute ducts and plumbing, and install the fan coil units. It proved to be the element that really gave long-term flexibility to the building. The subfloor allowed residents to move bathrooms and kitchens to whatever they wished, to rearrange ducts, and to repartition to space. In particular, the air intake and exhaust processes in the ventilation shafts involve heating or cooling the air through pipes installed beneath the floor before supplying it to the module's interior. Each module's MEP systems, located at the bottom, are interconnected to form Habitat 67's overall MEP system. The photo you're currently viewing depicts the convergence point of various pipes and conduits for supplying electricity and water to Habitat 67. Large pipes are installed throughout the external structure of Habitat 67, as visible in the photo. These pipes, responsible for the entire MEP system of Habitat 67, served as the basis for stacking the modules in an L-shaped configuration during construction. As mentioned in previous videos, the decision to stack the modules in an L-shaped configuration was determined by the positions of these pipes. The modules revolve around the main MEP pipe, responsible for the entire system, and the pipes of each module's MEP system are connected to the main MEP pipe. The modules at the top of the entire MEP system are designed to be connected to this main pipe at the bottom of the module's floor, repeating this structure multiple times to supply power and water to the top floor. In this video, we explored how waterproofing and resistance to wind and external air were addressed in each section. We also examined how vertical and horizontal alignment was achieved during the process of stacking the modules and how it was verified. Finally, we briefly looked into MEP systems within each module and the MEP system of the entire Habitat 67 structure. Additionally, we revisited the criterion for stacking the models in an L-shaped configuration, as explained in previous videos. Thank you very much for listening to our Team 7 presentation.